Dear students, let us continue our learning the course Automata Theory and Computability. We are in the 8th session of the module 4. So in this session, we are going to cover the topics linear bounded automata to deal with the context sensitive languages under the Turing machine. Myself, Dr. Suresha.d from the Department of Computer Science and Engineering of Canara Engineering College, Bantwal, Mangaluru. First, let us learn the differences between the context-free grammar and the context-sensitive grammar. The context-free grammar, what we have learned already in the module 3, that is, what are the rules for the context-free grammar will be, the left side of the grammar should be a single non-terminal, and on the right side we can have any number of terminals, non-terminals, or epsilon may be there. So if you remember, so we use this grammar for equal number of A's and the B's or the epsilon. So now this grammar we use for the equal number of A's and B's. So in this case, on the left hand side, we can have the only a single non-terminal, but for the right side, we can have any string which can be including epsilon. That is, epsilon means nothing. So we can have the or we can have the terminals, or we can have the combination of non-terminals. Such a grammars we call them as the context-free grammars. So if we go with the formal definition of the context-free grammar is a grammar where each production is of the form A derives W. So where A is a non-terminal and W is a string of terminals and non-terminals. Informally, a context-free grammar is a grammar where any non-terminal can be expanded out to any of its productions at any point. There is no such a rule that it should be preceded or followed by something. So no such rules. It can be expanded at any point of time. The language of the grammar is a set of strings of terminals that can be derived from the start symbols. So if I have the string as a B, so this can be derived as S derives A, S, B, then again S derives A, S, B, then the S derives epsilon. So this is going to give us that is at any point of time we can go for substituting the non-terminal. But when we go to the context sensitive grammars, in case of context sensitive grammars, the grammar will be of this, the grammar productions will be of this format. It will be as W, A, X, that will derive as W, Y, X. So this A is replaced with the Y. A is replaced with the Y. But in what sense? That is, A is to be followed by the W, and A is to be preceded with the W and followed by its X. If A, W, and X are there surrounding the A, only then we can go for replacing. Such a productions we call it as the context sensitive grammars. That is, the context sensitive grammar is a grammar where each production will be of the form WAX will derive as a WYX. A is replaced with the Y. Where X and Y are the strings of the terminals and non-terminals, and Y is also a string of the terminal. So in other words, the productions give us rules saying if you see A in a given context, in the context, what is the context? That is, A is to be preceded with the W and it is followed by the X. If it is followed in this context, then you may replace A by the string Y. If that context is not there, then you can't go for replacing it. If I have a which is followed by a B and the X, so now in this case I can't replace. I can't replace this Y. So to replace this A, this A is to be followed by the W only and then the preceded with the X only. Only in this circumstance, in this context, we can go for replacing it. So this class of grammars, it is unfortunate that these grammars are called as the context sensitive grammars, because it means that context free and the context sensitive are they are not opposite. They are meant for replacing. But in the context free grammar, we won't look at any context for the given non-terminal. We can substitute with any of its productions body. But for the context sensitive grammars, we need to look at the context. That is, it should be preceded with what and followed by what. If they are matching, only then you can go for replacing the given non-terminal. Such a class of grammars, we call them as the context sensitive grammars. The linear bounded automata, what we are learning now, are designed for handling the context sensitive grammars. Now let's move to our actual topic of discussion, linear bounded automation. So this model is important because this model deals with the context sensitive languages. That is, this model is meant for accepting or rejecting the context sensitive languages. So till now, what we have learned for the tape is of an infinite length. So we thought that the tape is of an infinite length, and were leaving the region of interest, the rest of the region we thought as the blank. That is, if I take up the example as A, B, B, then the rest of the regions we thought that it is a blank on the either end, and the tape we thought as a tape is of a infinite length. Tape is of a in tape is of a infinite length. So this is what the assumption for the standard Turing machines. Fine. So now to have some limitations for the tape, we go with the bounding that one. That bounded automation will be your linear bounded automata. Here the infinite storage is restricted in size, but not in necessarily the storage in comparison with the Turing machine model. It is called as the linear bounded automata because the linear function is used to restrict the or bound the length of the tape. So now for restricting the bound of the tape, here we use the two special characters over here. One will be your cut C and other will be your dollar. So these two we use it as a end marker over here. We use as a end marker for the tape. So now in this section, we define the model of the linear bounded automata and develop the relation between the linear bounded automata and the context sensitive languages. It should be noted that the study of the context sensitive languages is important from practical point of view because many compiler languages lie in between the context sensitive and the context free languages. A linear bounded automation is a non-deterministic Turing machine which has a single tape and whose length is not infinite. So this word you have to remember. So it is not infinite, it is a bounded one. That is a finite length. It is bounded by a linear function of length of the input string. The models can be described formally by using the following format. That is machine M. Then Q will be your set of states, finite set of states. Sigma set of input symbols, tau set of tape symbols, delta transition function, q naught start state, b blank spaces, f will be the set of final states. Adding to that one, we are adding two more symbols over here. One is your cut C and other is the dollar symbol. So this cut C is used for your left hand marker, is used for your left end marker, and the dollar symbol is used for the right end marker. Dollar symbol is used for the right end marker. These are the new additional things which are added to the standard Turing machine model. That is your cut C and the dollar symbol. So when we add them, then the resultant will be your linear bounded automata. And one of the important features of the linear bounded automata is it's a non-deterministic Turing machine. This non-deterministic Turing machine, which we learned in the previous video, so it states that for a given state, for a given input symbol, we may have more than one transition may be there. So like this, we may have more than one transition. Q naught, A itself, I can have the right movement, or I can go to the state Q1, A I will replace with X and the left movement. So how it can be written? So Q naught is the first state. Then on the A, I can go to Q1. This A I will replace with the X and the moment is left. So this can be one such moment. Or the other one, it can be I will be there in the Q naught itself. A I will retain as A itself, but I will have the right moment. Now for the Q naught on A, we have the two transitions over here. For the Q naught on the A, we have the two transitions. Now for the simulation of such non-deterministic Turing machine, along with a bounds on the input tape, we go for the linear bounded automation. Next, all the symbols have the same meaning as in the basic model of the Turing machines, with the difference that input alphabet L will contain two special characters. One is the curtsy and the dollar. The curtsy is used for the left end marker, which is entered in the leftmost cell of the input tape and prevents the read-write head from getting of the left end of the tape. And a dollar is called as the right end marker, which is entered in the rightmost cell of the input tape and prevents the read write head from getting of the right end of the tape. That is to limit ourselves within the our entering region, we are using the symbols cut C and the dollar. Cut C is used as our left hand marker and a dollar is used for our right hand marker. So we should take care that we won't come beyond the your cut C and the dollar symbol. So we are limited to use only within those end markers cut C and the dollar. Both the end markers should not appear on any other cell except the input tape. And the read write head should not print any other symbol over both the end markers. End markers we need to retain it and we need to continue it. You are not supposed to change the end markers. You are not supposed to change the end markers over there. So whatever the input we will take, the input should be length of n minus 2. Those two are the special characters. Those two are meant for the special characters. The length of the input string w, where the length of the w will be equal to n minus 2. That 2 is used for the two special character, two end markers, curtsy and the dollar. The input string w can be recognized by a linear bounded automata if it can also be recognized by the Turing machine using no more than kn cells of the input tape. Then where k is a constant specified by the description of the linear bounded automata. The value of the k does not depend on the input string but is purely a property of the machine. Whenever we process any string in linear bounded automata, we shall assume the input string is enclosed within the end markers, curtsy and the dollar. Now, in the model of the linear bounded automata can be represented by a black diagram, which we will show it in the next slide. There are two tapes will be there. So the first tape we call it as the input tape, and the second tape we call it as the working tape. On the input tape, the head never prints and never moves to the left side. On the working tape, the head can modify the contents in any way without any restriction. In the case of the linear bounded automata, an instantaneous description is defined by q, w, comma k, where q is a set of state, tau is the tape symbol, and k is some integer between 1 to n. The transition of the instantaneous description is similar, except that the k changes to k minus 1 if the read write head moves to the left, and k plus 1 if the read write head moves to the right. That is, if we move towards the left side, we decrement by 1, and if we move towards the right side, we increment by 1 over there. So that when we reach our 0, that is our curtsy, when we reach, we need to stop. The language accepted by the linear bounded automata is defined in this way. W, which belongs to sigma minus of cut C and the cut dollar whole star. Means your input should have a single copy of cut C and the cut dollar, and that should be present within the, your string should be present within these two, cut C and the dollar. Fine. And we start with the length 1 and we keep on continuing this. So when we end at Qi and Qi is in belongs to your accepting state, then we say that it is accepted or else it is going to be rejected. If you go with the block diagram of the linear bounded automata. So now here we have the two tapes over here. One is the input tape, other is the working tape. So in the previous standard Turing machines, the working tape concept was not there. This is newly introduced in the linear bounded automata. The linear bounded automata will have the two tapes. One is the input tape, other is the working tape. And in the input tape, you can see the special characters cutsy and the dollar. This cutsy will be my left end marker. Cutsy will be my left end marker, and the dollar is my right hand marker. Dollar is my right hand marker. So all your string should be there between your cutsy and the dollar. Your W is to be there in between. And the restriction for the head is head can't move left side. It should move towards the right side. It should move towards the right side. Means whenever we take any symbol, we directly won't work anything on the tape. Instead, we work on the, we'll put it on the working tape. There we process. Because it is a non-deterministic finite automation, we can have the n such options may be there. That's why the cell will be of size kn cells will be there. So that is we can have the k option for the given input symbol. We may have the k options for the given input symbol. So we can have the kn cells will be there in the working tape. So with that working tape, we need to process the given input. And this is how the linear bounded automation work. The main restrictions in the linear bounded automation is including the special characters cutsy and the cut dollar, which will mark the left end and the right end marker. Along with that one, there is a limitation on the input tape, input read write head. What is the limitation over there? The head can't move towards left side. It should always move towards the right side. But for the working tape, there is no such restriction over there. We can have the any movement is allowed for the your working tape, but not for the inputted tape. So this automation, this block diagram and the automation is the important feature of the linear bounded. This important features we call it as the linear bounded automation. Linear bounded automation. Right? The relation between the linear bounded automation and the context sensitive languages. The set of strings accepted by non-deterministic linear bounded automation is the set of strings generated by the context sensitive grammars, excluding the null strings. Now we give the important result, that is if L is a context sensitive language, then L is accepted by the linear bounded automation, and the converse is also true. That is if it is accepted by the linear bounded automation, then it is a context sensitive language. Now to summarize the things what we learned in this video. So we learned on the first two concepts. One is the context free grammar and the context sensitive grammar. The context free grammars will have the restriction for the context free grammar is the left hand side should be a single non-terminal. Left hand side should be a single non-terminal, and right hand side we can have anything may be present, and it won't decide on any context. Whenever we get this capital A, the non-terminal A, that will be replaced with any of the production body over there. But for the context sensitive grammar, so the left side will have the, we define the context over there. Along with the given transitions, we define the context as a W, Y and the X. So now the context is A will be replaced with Y only if it is followed by X, only if it is followed by W and preceded by the X. So if we have only the followed and the preceded by W and the X, only in that case we need to replace this A with the Y. In the rest of the cases, we are not supposed to replace. Then next to this one, we learned about the linear bounded automation. The linear bounded automation was designed for handling the context sensitive languages. So now the key features of the linear bounded automation will be the first one is the tape we will restrict by putting the two special characters. One will be the dollar, other is the cutsy. The cutsy we will put it to the put it as a left hand marker, and the dollar we will put it as the right hand marker. And our string should appear in between the cutsy and the dollar. And the second one, when we go to designing the linear bounded automata, there we consider the two tapes are considered. One, the first tape will be your input tape, and the second will be your working tape. First will be your input tape, and the second will be the working tape. So in the input tape, we along with the strings, we use these two special characters, courtesy and the dollar. And the working tape will be of the length k into n. And this is a simulation of the non-deterministic Turing machine. For the non-deterministic Turing machine, we may have the k such options may be present. That's why the length we will take it as the length of the working tape will be k into n. And the restriction for the read-write head is the head can move only in the right direction on the input tape, but it is not the case for the working tape. In the working tape, it can have any movement, but for the input tape, it should always move towards the right side. The references for these presentations are taken from the textbook KLP Mishra, N. Chandrasekharan, 3rd edition, Theory of Computer Science, PHI 2012. Thank you.